here in the corner. Expand this. Okay. Let me also, just talk about Piazza. So you should be able to, you should have received an invitation to Piazza, and if not, you can use this Piazza link posted in week 1. And sign up there. When you join Piazza, please make sure your account has your full name. Okay. So in the upper right-hand corner, if it doesn't have your first and last name, change your settings so that it does. Okay. And because Piazza is not integrated with my UCLA or CCLE or anything like that. And so just at the end of the quarter when it will produce a report in the statistics tab of basically how many people have participated and how many contributions you've made. And so anyway, I just take that report and I manually enter it into the gradebook. And so your first and last name need to appear, otherwise I won't be able to input it properly. Okay, and I've just written a few things here. Okay, so today we'll continue talking about data structures. On Wednesday we covered kind of our atomic vectors and our lists and factors, and then today we'll cover two-dimensional ones, which will be the matrix and the data frame, okay, which are very important. So matrices are basically atomic vectors that have a dimension attribute, okay? So if you create an atomic vector and you ask, what are the dimensions? If it's an atomic vector, it's going to say there are no dimensions. It's going to say null. But then if you create dimensions, then it will restructure the vector to be basically a rectangle, a matrix, okay? So here I have a matrix A with 3 rows and 2 columns. If I ask type of A, what will it return? What's that? Type of A will be an integer matrix, okay? So let's, so I'll go ahead and we'll do this here, okay? And if I say type of A, it will say integer, right? Because A was created using 1:6, which produces integers, and so now, and because it looks like this, it's a matrix, right? And if I ask for the dimensions of A, it's going to return back a value. It's going to say 2, 3. Does A have any attributes? What are the attributes of A? The attributes of A are the dimensions, okay? The dimensions are the attributes. Now if I suddenly, if I did this, what would happen to A? Does this do anything? Will this throw an error? Will it work? Okay, so I do that, and if I ask what does A look like, what does it look like now? It's an atomic vector, okay? Type of A, what is this? It's still going to be integer, okay? And if I ask for the dimensions of A, null, okay? Attributes of A, there's no more attributes, okay? We got rid of the dimensions. Okay, and then again, you know, if I wanted to switch it back up, I can say dimensions of A will be 3, 2, And A is now a 3 by 2 matrix. Okay, so all we're doing is we have an atomic vector and we apply dimension attributes to it. Okay, and that's what turns it into a matrix. Okay, so A is a matrix. I can get rid of the dimensions of A again. Okay, so A is 1 through 6. What would happen if I did dimensions of A is 4 by 2? Okay, it gives me an error. It says you can't do that, right? Because A only has 6 elements. A is a atomic vector, 1 through 6. What if I say dimensions of A is 1 by 6? Does this change A at all? Or does A remain the same? Okay. So what happens if I print out A? Will it look the same? Will it be 1, 2, 3, 4, 5, 6 in a row? Because I said the dimensions of A will be 1 row, 6 columns. Okay, so now it's different, okay? It is a matrix with 1 row and 6 columns. So these two things are different, okay? Because up here, if I asked what are the dimensions of this thing, it says there are no dimensions. If I ask what are the dimensions of A here, it's going to say it's 1 by 6, okay? So this is a matrix because it has dimensions. The other thing is not a matrix, it's an atomic vector, it has no dimensions. Those are the key differences, okay? Atomic vector has no dimensions. As soon as you have dimensions, it becomes a matrix or an array, all right? If you have more than 2 dimensions, it's an array. Okay, so I think these slides kind of cover a lot of these types of things. This is the integers 1 through 12, and we give it 3 dimensions, 2 rows, 3 columns, 2 sheets, okay? And it fills them out in this order. It goes, it fills down the rows, across the columns, across the sheets, okay? So it goes 1, 2, 3, 4, 5, 6, and then so it fills down the rows 1, 2, and then across the columns 3, 4, 5, 6. And once it's filled out this entire sheet, it goes to the next sheet, and it goes in the same order: down the rows, across the columns, across the sheets. Okay, 7, 8, 9, 10, 11, 12.
Would it create an error if you had only 6 integers but 2 sheets?
Yeah, if I said 2, 3, 2, and I only had 1 through 6, would it create an error or would it recycle? This is a good question. Let's try it out. Okay. All right. So this is what I have, and this is what B looks like. We'll do the same line. I think it'll error out, but I'm not sure if it'll recycle. Oh, it looks like it worked fine. Okay, so I'm sorry, it recycles. Okay, so it says we can do this. Okay, yeah, question.
Previously, when you set the dimensions to 2 and 4, why didn't it recycle that time?
I think it has to line up exactly for the recycling to work. So I think if I change this to like 1 through, let's say 12, and I did 3, 3, 2, which would need 18. No, it's recycling now. Okay. I guess, all right. I'm trying to think what's going on here. It must be during the creation part, we can do recycling, but then when we are modifying, attaching an attribute, it will not recycle. Yeah. Okay, that is what's going on. Okay, so here, if I say B is, we're getting into like really nitty-gritty stuff here. Okay, so B is the integers 1 through 12, and I can do dimensions of B is going to be the vector 2, 3, 2. Okay, this will work right here, and then we get an array. Okay, let me just drop the dimensions of B. Okay, so B is again 1 through 12, but here if I say the dimensions of B are going to be 3, 3, and 2, this will error out because the product of the dimensions don't match the length of the object. So it's in this function of assignment to the dimensions here. Okay, so I know it's a little strange, but that's what we have. Okay, so I guess in the creation of the array itself, it will handle the recycling. Okay, so I think I've demoed this stuff where you have the vector and you just modify the dimensions in place and it changes the shape there, and so that's in your notes. We have the length argument, okay, which will tell you how many elements are in here. So here I've got B, and I can ask what is the length of B, and it will say 12. Right now B is an atomic vector. Let me see here. I know you guys are squinting back there. Let me see if I can change.
Sorry.
No, that's let's see here. Okay, I don't know if that's any better, just a little bit. Okay, so here is B. We can ask what is the length of B. If I ask what are the number of rows of B, what will it tell me? It's going to say there are no rows to report back, because right now B is an atomic vector. I'm going to go ahead and change B into a matrix. So B is this. If I ask how many rows do we have in B, it will tell me 3, right? And the number of columns of B will be, not a trick question, 4, okay? And what is the length of B? The length of B is still 12, okay? It's you just have to think these atomic vectors are vectors with dimension attributes attached to them. One thing to note is that when I took my atomic vector 1 through 12 and applied the dimensions, the numbers get reshaped down the columns. Okay. So we go up, I guess, across the rows. Okay. So it goes, across the rows, then the columns. So it fills out across the rows and then the other thing. Okay. You can attach row names and column names. And you'll get that. And then I think I just demoed these. What's the length, number of rows, number of columns. Okay, similar for, here's an array, a 3-dimensional array. You can also give the dimension names. So not just row names and column names, but I guess sheet names. So we've got, the row names are 1 and 2, and the column names are little a, b, and c. And then the sheets are called capital A and capital B, or something like that. And this comes in as a list. Okay. So C, the combine operator that takes vectors and combines them together, can be generalized to combine column-wise or row-wise. So here A is the 2 by 3 matrix 1, 2, 3, 4, 5, 6 across A, B, and A, B, C like this. And if I do C bind, which is bind column-wise, then it pastes the two things together. And if I do R bind, it will paste, kind of combine them row-wise here. Okay, and that's what we have here.
They must have the same column names for R bind.
Let me think. I think R bind. Well, let's try it out. Anytime you have a question and I don't know, we'll just try it out here. Okay, so here I've got B, and we'll do call names of B to be, we'll do the capital letters 1 through 4. Okay, so B looks like this now. And let's make a copy of B, and we'll call it D. And D looks like this, and we'll change the column names of D to be lowercase letters 21 through 24, okay? And so D is UVWX. Okay, so here's B, here's D, and let's try to R-bind them. Okay, so when we did that, it just kept the column names of B, threw away the column names of D, and said I did it, okay? So D is that, and B is that, and it just ignored the column names. If I did it the other way, D then B, yeah, it keeps the first one will be, I guess, the primary, and it'll keep those column names, and probably the same thing for the rows, I imagine. Okay, good question. We took a quick look at this already, but you have so you have atomic vectors, which are one-dimensional, and then you can also have a matrix with just one row or one column. Okay, and so here is F, which will be an atomic vector 1, 2, 3. And when you ask for the structure, it says integer 1:3, and that's it. There are no attributes, and it's atomic. Okay. Here, I'm making a matrix with one column, and it goes 1, 2, 3. And notice when we ask for the structure of G, it's ever so slightly different. Here it just says 1:3 for F, the atomic vector, and here it says 1:3, 1. Okay, meaning we've got 3 rows, the rows 1 through 3, and 1 column. Okay, and then when you ask for the attributes, it does have attributes, a dimension attribute, saying there's 3 rows and 1 column. And is atomic didn't print out on the screen, but what is this going to say? Is atomic will be true, right? Because atomic refers to the idea that all of the elements in there are of the same type. Okay, so they're all integers here, and so it is atomic indeed. Here we make a matrix with 1 row and 3 columns, okay, by saying make a matrix of the elements 1 through 3, and 1 row, okay? And then when you ask for the structure, then it says there's 1 row, 3 columns, okay? So a lot of this information appears in the kind of the structure question. Okay, here we have this is technically an array, okay, because we say make an array out of the elements 1 through 3, and then the second argument in the array is going to be the dimensions here, okay, except here we only gave it 1 dimension, which was a 3. And so this thing looks almost like an atomic vector, but it's slightly different. There is something different. It says there's one dimension there, okay? And actually, if I ask what are the dimensions of I, okay, so here's I, and I ask what are the dimensions of I, or I'm sorry, not the dimensions, well, okay, well, what will this return? Okay, it's going to return a vector with the value 3, okay? And so if I ask what are the attributes of I, it's gonna say, you know, there is a dimension, okay? But it feels strange and because there's only one element, right? We're used to seeing rows and columns, but here it looks like this, right? So I looks like this, 1 through 3 looks like this, but this has no dimensions, whereas this does. Okay, and the only way we can really distinguish between these two is because here it says, you know, when you ask for the structure of I versus the structure of 1 through 3, here it says this is a one-dimensional array structure here. Let me take a note, and I should add attributes and dim to that slide 14. Okay. All right, so that's, I think that covers all I want to say for matrices right now. You know, we'll look at a bunch of operations and stuff, you know, matrix multiplication and things like that. And so far, all of our matrices have been numeric, or I mean integer, but of course matrices can contain decimals, floating point numbers. But you can also create matrices out of true-false values, matrices out of character strings as well, okay? So for example, here is our matrix B, but if I can just say is B greater than 5, okay? And now we have another matrix, and this is a logical matrix, okay, of true and false values, okay? Or I can say B per percent 2 equals 0, okay? And this will give me, you know, basically a checkerboard pattern of, you know, odds and even numbers. All right. Now we'll generalize to generalize the list, or not the list, but we'll make turn lists into data frames. Okay. And so when you do your data analysis, you're almost always going to be working with a data frame. Okay. Unless all of your values are strictly numeric, but you know, if you have columns of mixed type, if you got one column that's categorical and another column that's numeric, then it's going to be a data frame. All right, and the way a data frame works is that it is a list, and the list has vectors that are of the same length. Okay, so so that allows you to create a two-dimensional structure. Okay. So the data frame will have column names and row names, and but length for a data frame is going to be the length of the underlying list. Okay, so here we can create a data frame using the function data.frame. Okay, and I'll throw this over here, and so I'm going to say data frame is this. Okay, so here's my data frame. And if we ask what's the structure of a data frame, it says it's a data frame, but it's much like a list. Okay, if I say type of df, what will this return? The type of will say list. Okay, the class is a data frame. Okay, but so when you print the data frame, it's using print as a data frame, but I can kind of force it to print as a list, and it prints it out this way. Okay. So, you know, we can ask what's the first thing in the list, and we have these different things here. Okay. So data frame is a list. And when you ask for the structure, we see there's two elements in here. Okay, that's a list of two, an x and a y, and x is an integer vector and y is a factor with 3 values, 1, 2, and 3. Okay, The default behavior, as we see here, is that it takes strings and it turns them into factors. And so if you don't want that, back in your creation here, when we say data frame X is 1, 2, 3 and Y is ABC, you also have to throw in the option strings as factors is false. Okay, and then when we do this, it looks like this. It looks the same, but the difference here is that when we ask what's in my data frame, here we have integers and characters, whereas the default settings will create integers and factors. Okay, and depending on what you're doing, maybe you want the factors, or maybe you want the strings or characters. Okay, I think we saw this. The type of data frame's type is a list. The class is data frame, and you can ask, is it a data frame, using is.data.frame. All right, you can coerce objects into a data frame, right? So if you take a vector and you throw it into a data frame, it'll create a data frame with one column, right? If you have a list and the elements of the vectors in the list are of the same length, then it will create a data frame without complaining. Okay, but if they're not the same length, it's going to error out. And if you have a matrix and you throw it into a data frame, it will make a data frame based on that. Okay, so let me just kind of demo this. So here's B, and I can say data.frame of this, and it creates a data frame here. Okay, so here I'll call this DFB. So DFB is a data frame. So B is a matrix, right? So we can ask, what's the structure of B? And it's a matrix, right? Type of B is integer, okay? Whereas DFB looks similar, but if we say type of data frame B, oops, that's going to be a list. And with the structure of DFB, it's going to say it's a data frame, and you've got columns A, B, C, and D with these integer elements in it. Let me just show you. We'll create a list. We'll call L, and we'll make a list where A will equal 1 through 4, B will equal 11 through 14, and X will equal A, B, C, and D. Okay. So here is our list L. Each thing has 4 elements. The structure of L is integer, integer, character, right? And I can throw this into data.frame of this list, and it creates a data frame out of those things as well. Okay, and so I'll just call this DFL, which will be data.frame on L. Okay, so DFL looks like this. What's the structure of DFL? It's going to say data frame, 4 observations and 3 variables. Okay, and by default, it converts the characters into factors. So if we don't want that, so L being this list, when I create the data frame, I would have to say DFL is data.frame L, strings as factors false. And it looks the same, but the structure of DFL will maintain integer, integer, character there. Okay. Structure of the list is a list of 3, and so these are quite similar, but there's a few things that are different, right? Structure of a data frame will tell you 4 observations of 3 variables here. Okay. Over here, it says list of 3, that's where the 3 variables go. It becomes, the list of 3 becomes 3 variables. But because the data frame, all of the elements have to have the same length, okay, in this case 4, it can just say 4 observations, and you'll know each of these things will have 4 elements. Whereas in a list, you can have one thing that's 10 units long, 10 elements, and another thing that only has 2 elements, and so it's going to kind of tell you how many elements show up here. Okay. Yes.
Is there a reason you use equals instead of the assignment operator?
Oh, I don't know. I was just lazy, I guess. Okay, combining data frames can be done using cbind, okay? And so in order for it to work, if you want to do cbind, the new thing you're adding has to have the same number of rows, okay? And if you're going to do rbind, like you're binding 2 data frames together, the column names have to match up, okay? So earlier when we did rbind on the matrices, the column names did not have to match, okay? But when you rbind with a data frame, the column names do have to match, okay? And so this kind of talks about that here, okay? The number of rows must match, but row names are ignored. When combining row-wise using rbind, the number and names of columns must match, okay? When you're going to make a data frame, just don't cbind the vectors together first. Just throw the vectors directly into data frame, okay? Because cbind is generally a matrix operation, and so if I cbind this and this together, it turns everything into the same type first, okay? So it converts everything into a matrix, and in this case it's going to coerce everything into a string, and then you've got a character vector, and so cbind will turn everything into characters, and then you're data framing that, and you're going to get this funny looking thing. Over here, just throw the vectors directly into data frame, and it will produce a data frame. Okay, we've got a few things. So later on we'll cover the package dplyr, and in dplyr they use something called the tibble. Okay, and the tibble is pretty much the same thing as a data frame, except it plays a little bit nicer with the screen. So I don't know if you've ever experienced this, but you try to print out a data frame on the screen, and it like flushes the entire, like it fills everything out, and it goes like this, and you kind of have to scroll, and sometimes the output looks messy, right? Is it as.tibble? If you turn things into how do I make it dplyr? All right, let's just see. How do I make a tibble out of this? Is there a tibble function? Tibble on empty cars. Empty cars must. Oh, empty cars is, I'm sorry. Cars is a data frame, is that right? Yeah, okay, cars is a data frame. But that's not what I want. But anyway. All right, never mind. I can't do what I'm trying to do here. Basically, tibble, when you use a tibble, it's aware of how much real estate you have on your screen, and it's going to just print what it can fit, okay? Rather than flushing everything and having all of this text fly by. All right, is all of this okay? All right, we'll start talking subsetting, and we'll see how far we get in the subsetting section. There's a lot, and we'll probably have to continue it on next week. Okay, subsetting allows you to take whatever data structure you have and just pull out only certain elements of it. Okay, but it's a lot more than just saying I only want the 5th and 6th rows, or I only want the 7th and 8th elements. Okay, we'll start off with those basic things, but there's a lot of cool things you can do with just the simple subsetting operations if you just think a little creatively about them. Okay, so anyway, here's a vector. Okay, and they 2, 4.2, 3.3, 5.4. The 0.1 and the 0.2, 0.3, and 0.4 kind of show you that this is the 1st, 2nd, 3rd, and 4th elements, where, but they're not in order from least to greatest or something like that. Okay, so anyway, you can just say, I want the 3rd and 1st element, and we can see we pull out the 3rd and 1st element from that vector. Okay, you just say, using square brackets. Okay, so our vector is called x, and we just subset x using square brackets, and you can provide kind of a list of integers. You can ask for the order. Order is kind of the order that you would need to use in order to sort the list from least to greatest. And so if you subset x on the order, it's going to put them in order from least to greatest. Okay, I mean, this is silly when we have the sort function, but that's what the order does. So if you're kind of curious, which element is in 2nd place, okay, in order it's going to be the order says the 3rd element, right? And that indeed we see that the 3rd element is kind of like the 2nd place element. Okay, if you give it kind of duplicate indices and you say I want 1 and 1, it's gonna pull that element multiple times. Okay, and it has no complaints doing that. And then if you give it something other than an integer, like 2.1 or 2.9, it's going to just truncate them and treat these as 2s, and it's going to give you back the 2nd element. Okay, you shouldn't do this. This is a weird thing to do. Okay, but that's something to be aware of, which means you might do a calculation, and we'll talk about implications of floating point numbers, but you might do a calculation where you think the result is 3, but inside the computer it's actually 2.99999. Okay, and when it prints it looks like 3, but in reality it's not 3, it's 2.99999. Okay, and if you were to use that value to subset, it's going to pull the 2nd element rather than the 3rd element. Okay, and we'll talk about the floating point stuff later, but sometimes what appears on the computer is not what actually is. If you give it negative integers, okay, it's basically I want everything but these things, right? So I want everything but the third and 1st elements, and so it returns back the 2nd and 4th. But you can't say negative and positive because then it doesn't know what to do, right? It says I don't want the 1st one, I want the 2nd one, and then it says, well, what am I supposed to do with the 3rd and 4th? Because whenever I say negative, it usually means I want everything but this negative element. So it says you can't mix things with negative subscripts. With a logical vector, it will return only the values that correspond to true, okay, and it will recycle, okay. So here we got true, true, false, false, and it will return the first 2 elements, but not the last 2. And then here, x greater than 3 is a logical vector, okay, where it's true only for those where x is greater than 3. And so it's true for these 3 elements, and so you can subset using the condition using this, and it's going to give you back all the elements in X that are greater than 3. This is okay? This is subsetting using logical vectors is extremely important to understand and handle, okay? Again, here we will recycle, okay? So true, false gets recycled to true, false, and it returns the first and third elements, okay? And then if you have a missing element in your logical vector, or any vector you provide, it will always return missing, okay? Okay, if you put nothing in there, it will return the original vector. All right, it seems silly for atomic vectors, but it's especially useful when subsetting a matrix, because you might want like all the elements in a row. Okay, so you'll just specify the row number, and then you'll put nothing for which columns you want. So as far as which columns you want, you just put nothing there, and it will return all of the columns. Okay, and then if you subset using a 0, it will return a 0 length vector, okay, which is different from null. It's a vector with 0 elements in it. Okay, if things are named, so if you've got a vector where you have attributes, such as the name, and you name them A, B, C, D, or something like that, then you can subset using the names, using the character vectors. All right, and then just like integer indices, you can repeat them. Okay, you have AAA, and you get something like this. And when you use the single square bracket, the name has to match. Okay, so you can't, if the name is ABC and you call for something named A, it's not going to match. And it's going to say that thing is missing. Okay. All right. That's as far as we'll get for today. We'll stop here. We'll see you guys on Monday. Have a good weekend, and you know, get started on the homework. It's due in I guess 5 days or so. So we'll see you then.